Good morning, everybody. My name is Javier Echeverria, and today, along with my teammates Daniel Cortez and Andrew Emerton, we will be presenting on the Johnson & Johnson Capstone Project final demo. Before we begin to explain this presentation in detail, we would like to give a special thanks to both Dr. Christensen and Bill Femmer for aiding us throughout the course of this project and guiding us through it as well. For today's presentation, this is our agenda and structure that we will be presenting with. Background: Johnson & Johnson is an American multinational corporation that develops medical devices, pharmaceuticals, and consumer packaged goods. Because Johnson & Johnson is one of the top medical device manufacturers in the nation, they are a company that is heavily invested in emerging technologies that can facilitate the jobs of medical professionals. MRI machines. MRI machines are devices that use magnetic resonance imaging to form pictures of anatomy and physiological processes of the body, and then are commonly stored in what is called DICOM files. These DICOM files are composed of 2D images representing each layer of the anatomy that was scanned. Using appropriate software, medical professionals can then inspect each of these individually scanned layers. Oculus Quest. The Oculus Quest is a virtual reality headset and controllers that allow all applications to run natively on the device. Unlike other headsets, the Oculus Quest is an untethered headset, meaning it does not require to be connected to a PC to run. In addition to this benefit, the controllers also permit 6 degrees of freedom movement, which allow for a more immersive interactions for the users. A-Frame. A-Frame is a web framework that creates 3D virtual environments that run on web browsers by using HTML, CSS, and JavaScript. A-Frame is built on top of a JavaScript library called Three.js, which permits the rendering of 3D graphics in a browser environment.
All right, and now onto our problem statement. Can MRI scans be visualized using off-the-shelf VR technologies such that the MRI 3D model can be rotated, scaled, and moved in collaboration with other people in remote locations to be able to locate and characterize abnormalities in the scan? Our solution will answer this problem by fulfilling a series of requirements. All right, and the first requirement basically considers the first thing the user has to do in this process, and that would be converting their folder of a bunch of 2D MRI images into a 3D model in the correct format that we can deploy into an A-frame virtual environment. And our acceptance criteria for this basically is the user can run this DICOM3D Python script in their Linux command line where they have a directory called MyScans in there that has all those 2D images, and then that will generate the 3D model that will be in a local output folder. The next requirement is that the user needs to be able to load that 3D model into the A-frame virtual environment so they can actually analyze it, in that collaborative environment with the other users. The acceptance criteria for this is that the user can just, in that same Linux command line, they can run a deploy model.sh script that we have that will deploy that 3D model into the A-frame environment. The next requirement basically is can we see other users in that virtual environment as well as their interactions with the environment so that anybody in there can collaborate with the models that get uploaded. The first acceptance criteria for this basically is when users get in there, can they see other users in the form of their avatars, which is basically just a low poly face with randomly, colored bow ties that they have. Along with that, if one user performs an action, can all the other users in the instance also see that action real time? All right, in this requirement, does the user have a way they can use an input device to point things out on the model? And the acceptance criteria being that users will have multiple colored shapes they can manipulate by grabbing, moving them, and they can do this anywhere on the 3D model, basically anywhere in the environment, so that just includes being able to place them anywhere on the model. All right, and the next requirement is the user will want to be able to move the 3D model in VR so they can provide a better view for them, for themselves as well as other observers in the instance. Acceptance criteria for this being that users can physically, like with the controller, grab onto the 3D MRI object, with the controllers and move them anywhere in the environment. All right, and next requirement is as a user, they're gonna need to be able to scale that 3D model bigger or smaller in VR. They'll do this so they can bring any region on that model into more focus just by enlarging it. Acceptance criteria for this being that users with the Oculus Quest controllers can grab objects with both hands, aka both controllers, and pull the object apart to scale the object up, make it bigger, or push their hands together with it to make it smaller. It's kind of like pinch to zoom on phones. All right, and the acceptance criteria being that users will have two buttons. One is for horizontal rotation, one is for vertical rotation. This is with like a user interface type thing that we just deploy into the environment that lets them rotate it these ways. And that is all for the requirements.
And now we will begin our demo where we will show how a user can turn their 2D MRI images into a 3D object and deploy that into the A-Frame virtual environment as well as interact with it with other users.
Okay, so here we have our directory with all the files to start the conversion from the DICOM to the 3D model. Over to our left is our Linux terminal that we're going to be using to run the files. As described in requirement 1, MyScans is going to house all the DICOM files we're using. And I'm just going to show you one. Let's show you 208 or 285. There we go. So that's a piece of the shoulder that we're going to be processing in our 3D algorithm. So if I go here and run the Python 3 DICOM file as described, it's going to start the conversion. And this is just info, so the hue values for the data processing. So we can see here it's 376 pixels by 512 by 512. Drawing. Okay, and there's a very rough image of it. And there's a detailed image. Okay, so it's all saved now. Described in the requirements, we can now upload it with the deploy. So let's run the deploy.sh. It's just warning us that we already have that folder. Commit. Okay, and that's because we had the same files last time. So after the image has been uploaded, we can check it on the web. And here we can see the object was loaded as a GLB or GLTF. Also, if I load into the world, we can see right over here that this is the model we uploaded, and it's named as such.
Moving on to the next requirements. We can see other users and their corresponding interactions as well. As you can observe in the video, I am accessing this application through my mobile device and using touch controls to interact with the world around me. You can also do the same accessing through a PC or through the Oculus virtual reality headset. The benefit of accessing this application through the Oculus is that the Oculus is paired with two controllers that allow 6 degrees of freedom movement, allowing for a more immersive experience. As you can see here, I am grabbing objects in the virtual reality environment with my controls. And here I am gesturing to my teammate as well. For requirement 4, we are required to use shapes to point out things on different models in our virtual reality environment. This will facilitate the functionality of pointing out key areas in different models like I am doing right there. Here I am grabbing a red sphere and indicating another location on the model. For requirement number 5, users should have the ability to grab and move 3D models. This functionality is only limited to the Oculus Quest due to the 6 degrees of freedom movement that the controllers allow them. Using these controllers, users can grab models and move them in any direction within the 3D environment. For requirement 6, users should also have the same ability to scale models up and down. Using a two-handed gesture functionality with the controllers, users can make models as big and as small as they want. For requirement 7, users should also have the ability to rotate models. In order to allow for cross-platform functionality of this rotation among all users, you can see that we use the button to do that. Here you can see I am in the team with other members, and they were moving around as well. We proceed to toggle the skeleton and proceed to use the moving functionality as well. So I can show the skeleton and observe its condition with my teammates.
To convert the MRI images from 2D to 3D, we are using the iterative algorithm Marching Cubes. For this, we are using Python, and with the diagram below, you can see, first of all, there's the images. Then through the scan, it's making these point vectors and connecting them. And then on the right, we can see the 3D representation of the start of a 3D model, and then on the bottom is the full 3D model. After we create the model, we are then making our environment so that we can host it. So for this, we're using A-Frame, using HTML. HTML is what hosts the environment and allows when every user logs in, they immediately load into it. And then after that, loading the MRI images into the environment, we're using scripting. So we are using the environment somewhat like a GitHub. So we commit changes and then push the 3D model onto the environment. So with input mapping, we allow for the controllers of the Oculus Quest, the touchscreen to be tapped to move, and we also allow for mouse and keyboard, so WSD support. As you saw in the video, the only users that can move objects are ones with the Oculus Quest. But we also have virtual buttons that they can also interact with, as also seen in the video, for rotation. For collaboration in the A-Frame environment, we're using WebSockets provided with Firebase. So to allow for players to join from any device, once a player connects, they're connected to the WebSocket in the main server in Firebase, which allows tracking for position, color, rotation, and other attributes so that everyone can see each other's interactions in real time. Constraints. Our two main constraints are the computational limitation and A-Frame itself. The computation limitation is based off the hardware of the Oculus Quest. Since the Oculus Quest is running essentially a smartphone CPU, and this limits us graphically. A-Frame doesn't have the support as would Unity or Unreal Engine would have for something in VR. Our applicable standards include many different programming languages, web guidelines, and medical standards. These include JavaScript, Python, HTML, DICOM, WebXR, Marching Cubes, and HTTP. And lastly is our trade-offs. So we had to choose between accessibility versus computational power, and we chose to make it cross-platform for everyone, which means that it had to run on the web. Second is our client requirement versus customization. Some of the things that we've done could have been done in Mozilla Hub, but we were looking for our own environment to allow for the upload to be seamless. Another constraint was the documentation for A-Frame. Since it is still very new, there's very little documentation and support for any of the services provided on it.